Hey everybody, welcome back. Today we're going to be working on question 5 of the winter 2022 midterm exam. So this question is about processor performance. And so we're going to be looking at, for the LC2K ISA, performance for a single cycle, multi-cycle, and 5-stage pipeline design. So let's just go ahead and jump into it. Okay, so the first question asks us to calculate the minimum clock period in nanoseconds for the following designs. So we have a single cycle, multi-cycle, and again, the pipeline. So, well, what do we know off of that? Well, we know that the way we calculate or what determines the clock period for a single cycle is the amount of time that it takes for the slowest instruction to execute. Right. And so if we want to be able to determine how long the clock period is for a single cycle design, we just need to determine the slowest instruction. So how do we determine that? Well, I think I've mentioned this before in the class, but if you haven't heard it, in the traditional LC2K ISA, there's only 2 potential instructions that could be the slowest. And those instructions are the load instruction and the store instruction. Why is that? Well, we'll take a look at like what a load instruction does and what a store instruction does. So a load instruction does one register read or one stage of register reads, one register write. It does ALU computation. It has 2 stages of reading memory, right? Because it needs to load the instruction in the first place, and then it also needs to read whatever the value is for memory. It does not write memory, right? And then it does one of every traditional operation that we really consider. A store instruction, right, also reads registers. However, it does not write registers, right? And it performs an ALU. It performs one memory access, read memory access, and it performs a write to memory. So essentially, right, if I want to if I want to determine which one of these is going to be slower, right? So I don't really need to care. If I switch colors real quick. I don't really care how long it takes for a register read to occur. No, it's not what I wanted. Okay, let's switch back to blue. And then I'm gonna say done, and then so we don't really care how long it takes for register reads. We also don't care how long it takes for ALU because it's going to perform the same transactions on both. However, and we can kind of discount one of the read memories, right? Because load is only going to perform one more than a store instruction. And so essentially, if we're comparing the read mem plus the write reg time to the write memory time. So whichever one of these is greater is going to be the instruction that is slowest. So the reason we don't really have to consider adds or nors or no-ops is because all of those instructions are going to perform less transactions or are going to have less stages that involve accessing, reading register files or writing register files. So all of these are, if I had like if I had all the rest of the instructions here, they're all going to be less than the number of transactions that occur in this. So what we really need to consider is which one's going to be bigger. So read mem plus write reg is going to be 60 nanoseconds, and just writing memory is only 10. And so we're going to say that loads are the slowest instruction. And so how much time is it going to take? Well, there's 2 read memories, so that's 2 times 50. plus one LU access, one write register stage, and then one read register, and that'll give us 130. So the clock period for our single cycle design is going to be 130 nanoseconds. Well, remember in multi-cycle, we split up our pipeline, or we split up the access patterns, and we split up the architecture, and therefore, the clock period is determined by the slowest stage of our multi-cycle design. And so now we don't have to worry about how long each instruction takes. We need to worry about how the slowest part of this, right? And so the slowest part is definitely going to be the read memory here. And so our multi-cycle is going to take 50 nanoseconds. So a pipeline is very similar to multi-cycle. We're going to be splitting up our architecture into a bunch of stages. It's just the way we're going to take advantage of that is going to be different because we're going to try to execute instructions in parallel almost, right? And obviously there's hazards and such, but as a result, our pipeline is going to have the same clock period that a multi-cycle design is going to have. So it's going to be 50 nanoseconds. So that was part A. Part B says, an engineer tries to run a program with only these instructions. 50 adds, 50 stores, and unknown number of loads. The program takes 750 cycles for a multi-cycle processor. How many load instructions are in this program? Okay, so when we're trying to calculate the number of cycles that a multi-cycle processor takes, recall that we take the type of instruction, or sorry, let me undo that real quick. We take the number of an instruction type, right? So if in this case, for example, we had like 50 adds, right? So do 50 times the number of cycles for that instruction type. And then we add, we have a sum for like, each instruction type. So because we have 50 adds, so we have 50 adds, adds take 4 cycles, stores take 4 cycles, and loads take 5 cycles. So we have 50 adds times 4 cycles each, plus 50 stores times 4 cycles each, plus let's just use a variable because we don't know what that number is. We'll call it n, right? N times 5 cycles, and the total we have is 750. So from here, it's just a bunch of simple algebra. We're going to get 400 plus 5n is equal to 750, and then from there we get I subtract 400 from both sides, divide by 5, and I think if I'm doing my mental math correct, we'll get 350 and then 70. So we're going to have n is equal to 70. And so we're going to have 70 load instructions. Awesome. So that's part B. Part C, excuse me. Part C asks us what the execution time is in nanoseconds for this program on a 5-stage LC2K pipeline processor with the clock period calculated in part A. So, what we found in part A is that our pipeline takes 50 nanoseconds. To execute. And because there's no hazards, right, we're going to have a CPI that is really close to 1. The only reason that we're not going to have a CPI that is equal to 1 is like is what I kind of call like the boot up cycles. For example, if I was just running one instruction through a pipeline processor, right, it's not going to take 1 cycle. It has to, propagate through the entire pipeline, right? So it's going to take 5 cycles. So if you only had 1 instruction, your CPI is going to be 5. But if you had like 2 instructions and you had no hazards, your CPI, you would get you'd only take 6 cycles, right? And so your CPI would drop to 3. And so the number of cycles that I kind of call the boot up cycles is the length of the pipeline minus 1. Excuse me. So the length of our pipeline is 5 stages because it's LC2K pipeline. And so we're going to have 4 of those like boot up cycles. And so the number of cycles that we're going to have is the number of instructions. So we determined we had 70 loads in the last part. 70 loads. We have 50 ads, 50 stores, right? And so the number of instructions that I have total is going to be 170. So the number of cycles it's going to be, so I'm going to assume that because there's no hazards, each of those instructions are going to take an additional cycle, plus the 4 boot up cycles. And so the total number of cycles I'm going to have is going to be 174 cycles. So now I have I know this program is going to take 174 cycles. I know that the clock period is 50 nanoseconds per cycle. And so if I want to find the total number of nanoseconds, I can multiply these 2 numbers. So I'm going to have 174 times 50, and that's going to be equal to 8,700, I think. Yeah. 8,700 nanoseconds total. But I apologize, I kind of did that diagonally, but those are our final answers. And I believe, yep, that's all of number 5. Hopefully you found that helpful, and hopefully I'll see you guys next time with question 6.